I was planning to send to the list. My draft. And yeah. So the mailing list is this one, right? And to launch.
MSC.
No. Just yeah, you can check. If we find the room. Yeah. So I hope it will be sent. So normally I send email right now. If you can check. And so I attached this presentation and the next one, and I gave you a link to download the Python files for the exercise.
Professor, I didn't get any more.
Oh, yeah, maybe.
Clear MSC. That is C1.
Is this one? M2C.
Clear MSC.
Ah,
No, that's not either one.
they changed. Okay. Okay.
Normalement c'est M2.
M2.
M2 M2 at. Ah non, c'est pour tout, M2 c'est pour
Okay.
pas le tout premier, M2 c'est.
Yes, I sent it to MDC. Maybe. Is Raphael here? Okay. Maybe I can send it to you because you already sent me an email at some point. I send it to Raphael. Can you
I will
forward it?
sure.
Yeah. I'm sorry. I was thinking M2 was supposed to work. Okay. We can start now. So as you may know, data is everywhere. So here they reported some figures. Like on Facebook, there's 10 million photos uploaded every hour. On YouTube, it's like 1 hour of video uploaded every second. So that's a huge amount of data. And if you are familiar with big numbers, you can check zettabytes. It's a huge 10 to the power 18, I think, if I remember well. So 10 to the power 18 bytes around 2020. So that's a lot. Basically, we'll see in civil engineering and concrete science, it's quite different. Actually, there's a lot of scientific articles, but not that many databases. So there's different types of data, text, numbers, graphs, tables, images, videos, and all of these type of things. So basically, we are all means of getting data are same if you go on construction site or things like that. Some companies are now installing videos, recording a lot of things, like if workers are holding helmets and things like that. So how to process data? So this very general framework is used. It's very generally in a lot of data studies. So first and foremost, data collection. So in civil engineering, for now, in my opinion, it's the hardest part, because data is not shared among many people. So then once you collected data, you should prepare data, so either cleaning, so what we mean by cleaning, it's like removing some inputs or entries. For example, if the test results are relatively strange. Feature engineering, so it means you can add some descriptors. For example, if you know like compressive and flexural strengths, you can infer tensile strengths for concrete. Then some representative or representations to reduce dimension. For example, if you use images, images are high dimensionality data, so you should reduce dimensionality, like to remove some unnecessary information. So you can use clustering or things like that. And then in most of the studies, machine learning algorithms are used to predict something. Okay. So, maybe at least the oldest example in concrete science is the prediction of compressive strength. So that's what we'll try to do after this presentation. But now we can, a lot of people predicted a lot of things, like cracking patterns, shrinkage, things like that. And in the end, a very important aspect is visualization. So some people are specifically are doing mostly visualization, because representing results is part of the problem. So some examples of applications. So from real world, spam filtering, fraud detection, detecting faces in images, or a lot of things, not only faces. Medical images, search engines, etc. So when we do machine learning, most of the time, machine learning is interdisciplinary, so it means we are dealing with a lot of people. So personally, I worked with all of this type of guys, from biology to economics. So what's the difference between machine learning and statistics? So if you only do statistics, you're mainly using these tools, like maybe PCA or analysis of variance and over. If you're doing machine learning, you try to predict something. Okay, so most of the time people are doing statistics first, and then they do machine learning to try to predict something. So if you use machine learning, you can use one of these type of algorithms. So maybe neural networks, but support vector machines or decision trees or other types of algorithms. We don't really care about this. there's two main types of algorithms. The first one is called supervised, and second one is called unsupervised. So if you perform supervised machine learning, you basically give what we call training data to your algorithm, and you try to predict something, okay, which is called the output or the label. So for example, X can be the size of your concrete sample, the mix composition, etc. And you want to predict compressive stress in the end. Okay. So because you give the algorithm some data which are labeled, basically it's called supervised, because you teach your algorithms how to predict something. So here a very famous and basic example about fruits. So with length, width and weight of some fruit, you should predict the type of fruit. Is a banana, orange or apple?
My connection is not working. I go outside.
So for supervised learning, you're using labeled data, and for unsupervised learning, it's completely different. You try to learn something or group data points from unlabeled data, so it's like completely different. So unsupervised learning, you can write like this. You have some x values from real numbers, and you try to like cluster, like make groups of based on these values. Like find similar attributes in like a population, species, or concrete samples like this. So, for example, if you have two dimension, if you represent two features, you see here that there might be there might be two groups, okay, because there seems there's a small gap somewhere around here. So if you use some nice algorithms, you can make and represent these two groups. Okay. So some algorithms like K-means, Gaussian mixtures, etc. So for supervised learning, you actually train your algorithm, so you can tell your algorithms these things are, I don't know, bananas, and these things are oranges, and because it knows this, it can then make the groups. Okay, so it's like easier. And if you just ask to plot what we call a decision boundary. In supervised learning, this type of problem is called classification. So classification is when you try to predict the output within a given number of solutions. Okay. So if you try to predict concrete consistency in Europe, it's from there's 5 classes, okay, S1 to S5. So this is a classification problem. Okay. If you try to predict compressive strength, because compressive strength is continuous value in a given interval, it's not classification, it's prediction, interpolation. You can do nonlinear classification. So if you represent in 2 dimensions this kind of data, you see that it's almost impossible for an algorithm to find the inner part of this, because it's included in the blue dots. But yeah, sometimes you should manage to represent in using other dimensions to easily classify data. So what we call regression, like compressive strength prediction, you have some features. So most of the time you have many features, okay, but if you represent the output y given one feature, maybe if it's an interesting feature, you can get something relatively smooth. So here, based on this feature, you want to predict y. Well, here, just using this feature, it might not be that easy, but it's quite helpful still. So maybe you know linear regression. Okay, linear regression is just drawing a linear fit in one or many dimensions. You can use like polynomial regression. The same as you already did, I think, before. And you can use many types of regressions, like this one. It's a very high order regression, so it's very sensitive to noise. Okay. So how to select the best regression? Just keep this. It's not very interesting. You should how to select the best algorithm. We should, as I said before, train the algorithm. So when we train the algorithm, we use what we call a loss function or a training error. So this thing is like calculating the difference, or something related to the difference, between the actual y value, okay, because it's a supervised algorithm, you give the y value, and the f of x value, so a prediction. Okay, so you calculated an error between the actual value and the predicted value on the train, what we call the train set. So you can use least square or many other functions. And then we hope that on the test set, so it's the second part of your data set, the error will be small too, but it's not because the error is small on the training set, so like 80% of your data set, but it will be small on the test set. Okay, it's not that simple. So maybe the most important figure is this one. Yeah, and they said it's important. If you have here they represented, depending on the complexity of the model, the prediction error. So it means the error either on the training set or the test set. Okay. So if you give a lot of data to your algorithm, the more complex the algorithm, the smaller the error on the training set. Okay, because it will basically fit very well your training data. Okay, because you have all the outputs, and yeah, if you have many inputs, you can fit very well your outputs. Okay, just making things like this. You make the red model, you see it fits very well the training data. Okay, the red one. But actually, it's not the most effective one. Why? Because if you test on the test set, so it means the test set, you only give inputs, and you want to predict outputs without giving the original output, the actual outputs to your algorithm. So of course, if your algorithm is very simplistic, the error is still large. But like if you have a linear regression, but if you have like a polynomial regression, you have a better fit. Okay, because many problems, theoretically, all the problems can be approximated using polynomials. So if you use this kind of models, you decrease the error. Okay, because you have better description. But if the order of your polynomial is too high, you can end up with this type of fit, and of course it's not predicting very well unknown data. For example, if you add circles, data points in somewhere here, it will not fit very well. Is it clear? So basically, I think you should experiment this to really understand why it's working like this. It's not it's not proved it will be like this for all types of problems. Basically, many times it's like this. So that's not. You should not use the most complex model in all situations, basically. Okay? If you have images or high dimensional data, of course you should use very complex models. Okay? But if you have low dimensional data or not so many, or a limited data set size, okay, most of the time relatively simpler models can work well. And I think so what we have here is called overfitting. Okay, so it means there's a high variance in the predictions. Okay, so basically your model is very sensitive to noise. Okay, to very small variations in your data set. So it's basically overfitting your training set. So it cannot generalize very well on either the test set or a completely unknown data set. So how to avoid overfitting and know and make sure your model is not like this. Actually, it's not that easy. So there's several ways to try to avoid overfitting. First, reduce the number of features. Like if you get data from a concrete manufacturer, many manufacturers, they monitor temperature, okay, when they mix concrete. Actually, the temperature during concrete mixing is not that influent on the compressive strength at 28 days. Okay. So if you have this information, maybe it can be relevant if the temperature is ranging from, I don't know, -10 to 40 degrees. But most of the time, if it's ranging from like 10 to 25 degrees, as we have here, it's not useful at all. Okay, so you should just get rid of this information. Select the right model, so that's why we are doing this course. And use what we call regularization or cross-validation. Well, I not go into details, but basically how to regularize. What we mean by regularization is when you know that some inputs will not have unnecessarily large impact on the outputs. Okay, so we should regularize. Cross-validation is like in medicine, you should validate several times. Okay, otherwise it's not that precise. And I don't go into details. So how to split your data set? So I explained we always have at least a training part and a test part. Okay. So with the training, you train your algorithm, so you give the algorithm the output, the y values, and the test part, you just give inputs and you want to predict outputs and measure the error. Okay. Sometimes we have what we call validation set. This kind of set is useful for neural networks, for example, because how to train a neural network, you're making several loops, okay, and every loop, say, you partially validate your results, okay? And in the end, once you did all the loops, you verify and measure using the test set, okay? But if you use like linear regression, you do not make these loops, okay? So you don't need validation yet. And I think it's all. So yeah, they added some slides about cross-validation. I'll not go into details, but and metrics, maybe just these are. I should add something. These are metrics for classification problems. If you do regression problems, you can use metrics like R squared. I think you're familiar with like R squared. You can use what we call root mean square error and things like that. Okay. So I think you know R squared because you practiced fitting. So R squared is like a way to evaluate the quality of fit. And root mean square error, it's like an error, like Euclidean distance. So before doing the exercise, I just show you some references. So well, just to so that you know that there's many studies now. So I think this the first paper about the use of machine learning for concrete science in concrete science was the prediction of compressive strength. So it dates back to 1998. So it's almost 30 years old now. So a lot of papers have been published for almost 30 years now. So yeah, like more than 10,000 papers, I think, have been published on compressive strength prediction. It's a huge amount of papers. Other papers, like hundreds, have dealt with flexural strength of like high performance concrete, recycled aggregate concrete, etc. So many papers, like tens of thousands, have been published on predicting mechanical properties and more particularly strength. Some studies have been published about shrinkage, creep prediction, and actually we published quite some papers with my colleagues about shrinkage. I think, yeah, we published like 5 years ago, almost 5 years ago now, a paper changing the way people are dealing with shrinkage data. So before our paper, like less than 10 papers addressed the subject, and now, I don't know, hundreds of papers have been published, I think. So that's good to see people have changed the way to deal with this kind of data. Other people, they focus on fresh properties. Some people, they try to predict slump or this kind of fresh properties only based on the mix properties, for example. Some other people, they use cameras in mixers so that to eventually adjust concrete mix during mixing so that we can better get the right fresh properties. So I just reported 2 references, but now there's many, maybe tens of references. And other people, they do what we call durability, like carbonation, sulfate resistance. I was into that, well, we published articles about sulfate. And there's actually some RILEM. I don't know if you already heard about RIDEM. It's a big international association, and I'm still part of a working group on durability properties prediction. So we published review papers now that a lot of people are doing durability predictions. So these are concrete properties. Some studies have been published on image analysis. Okay, and I think the first studies published about image analysis, they focused on crack detection, like detecting cracks in either structures or structural elements or bridges or roads, things like that. I think in the early, almost 20 years ago, the first papers were published, and every week, like 10 or 20 papers published on the subject, so that's quite crazy. So here we never published about crack detection because honestly to find something new to publish is quite hard. So we published on like alvoids quantification. So as you may know, alvoids are quite important in concrete regarding freeze-thaw resistance. And it's actually quite hard to find alvoids in concrete slices. So we did, because I'm also doing a lot of microscopy and image analysis, we used neural networks to find alvoids in concrete. So I reported some references here. And some people are doing SEM images, scanning electron microscope images, to either predict macro properties, so they take images at small scale and they try to predict either durability or strength, or at least find all the phases in concrete. And I know you have some non-destructive courses with guys from University Gustave Eiffel. So for example, AI can be used to interpret radar results. For example, images they can be used for ultrasound images. So either in concrete, in geophysics. So some experts like, I think you already have some courses with Odile Abraham, they use ultrasounds a lot. And they collaborate with people, for example, like me, to develop this kind of models. So some very interesting papers have been published recently. And in robotics, so I think you know some companies are developing robots for almost everything. So that's the same in civil engineering. There's actually many papers concerning the use of AIs for robots in industrial environments. So I just reported one, but you can find thousands. You can also use some robotical approaches in material testing. So some people, and here we also published a paper to explain how to use AI to help a machine to find the right interesting way to test materials. So we did this with nano indenter. So basically, we used this kind of approach. So exploration, exploitation. It's like the same as a vacuum cleaner, for example, in a room. You can manage to use a machine using AI to cleverly explore an environment. that's all for references. I tried to give you quite a broad overview. Of course, you can just, I think, click on the links and find the papers, and at least look at the images. We try to publish nice images. So now we try to do some predictions. Yeah. So normally in the email you have a link to this folder. Maybe you can open the folder. Yeah. So to this folder, so there's 4 files in the folder. So there's a README file. So README, it's just a project description. So MD stands for Markdown. There's an I don't know how to say it. Like a notebook. This is a notebook. Okay. This is a Python file, but it's interactive Python notebook. Yeah. This is the way. There's a classic Python file with all the utilities you need, and there's a CSV. So CSV contains the data you will use. So you can basically download these files, okay, and you can put everything in a folder. So here I have a folder with all these files plus these things, and I just open in the README. No, at the beginning of the in the README I just explained. These are some basic models.
Working?
Yeah. So how to use it? I think you have on the computers you have what is called Anaconda. If you look for Anaconda in the Windows search tab, you can find Anaconda prompt, I think. Yeah, Anaconda. Oh, yeah, prompt. So if you open Anaconda prompt, so Anaconda is a software to manage what we call environments. So environments are closed, closed spaces. So in this environment, you can install whatever you want. Okay, basically without interfering with your system. So if you open Anaconda prompt, you can just type this instruction. So conda create so it's to create a new environment, basically. So you can find the same instruction on the web, but so Basic AI is the name of the environment, and pandas, numpy, scikit-learn, all these things are Python libraries that are useful in machine learning. So is it better? Maybe I can open. find the Conda prompt.
C'est une fois la commande de taper ça.
Yeah, Conda, no, you should type Conda create n for new. Then the name of your environment. So it can be anything. And then pandas, numpy, scikit-learn. All these things are libraries. So I put many libraries. Actually, you don't need all these things. At least you can do a lot of machine learning with these things. So I have been using your method. I don't think you have an Conda create. No, no, type Conda. Then the name of your environment. And then pandas, numpy, scikit-learn. And then it's installing a lot of things. Yeah, once you created, you should put everything in a folder. And normally with right click, you can open VS Codium, because I think VS Codium is installed in your computer. Yeah, like for VS Codium. Where is your folder? Yeah. No, you should place it in Z folder. Not yeah, not in download. We can open. It's not safe. I would say. You can actually so you have VS Codium. How did you find VS Codium? Vous avez trouvé où?
Je sais ce que vous avez dit, j'ai fait ça. Ça me paraît.
Okay, nice. Okay. So yeah, actually you should put everything in a folder in your Z storage space. So it's your personal storage space. Okay. And then using right click on this interactive Python thing, open with and VS Codium.
Comment on vérifie ça?
Yeah, there's long. Yeah, we should be installed.